Okay, so in this video, we're going to talk about covalent bonding. Covalent bonding belongs to a category of interactions that are called intraparticle attractions, which means this is the attraction between individual atoms that are brought together to make a compound. These intraparticle attractions are very, very strong, and we are going to compare and contrast those in a future video with some intermolecular attractions, which comparatively are weaker. So covalent bonding is the type of bond that is formed by two nonmetal atoms sharing electrons. So remember when we were talking about covalent nomenclature and we were using all of those prefixes, mono, di, tri, tetra, those were nonmetal compounds. And because we are using covalent nomenclature, we're also going to be using covalent bonds. So this is where they share electrons. Within the bond, the electrons can either be shared equally or unequally between the atoms. And how they are shared is based on the electronegativity of the particular element. So if you remember from our unit on periodic trends, we said electronegativity, which was an energy trend, increased as we went across the table and decreased going down. So the elements with the greatest electronegativity are going to be located over in the area where fluorine is, and the ones with the lowest electronegativity are going to be located in the area where francium is. And so elements that are highly electronegative are going to hog, for lack of a better word, the electrons. The electrons are going to spend more time with those elements and less time with the thing that they're bonded to. And so when those electrons are shared unequally, we describe the bond as being polar. We'll think about polar. If it has poles, that means it has two different areas, right? We have North Pole and the South Pole. Well, this would be a positive pole and a negative pole. The positive pole is the side that has less attraction for the electrons, and then the negative side is going to be the side that's hogging the electrons. And that's a partial positive and a partial negative. The fact that it's a partial positive and a partial negative is one of the reasons why we're going to see some differences when we talk about intermolecular attractions a little bit later. Nonpolar is where the electrons are shared equally. So there are no poles, right? Everything is equal. There's no positive and negative end. They're just shared equally, equitably between the two parts of the bond. Okay? So because the electrons are physically shared between the atoms are connected, and we see that they form characteristic shapes based on the valence electron configurations of the atoms involved. Remember that the valence electrons are the outermost electrons, and when we're talking about our representative elements, these are the ones that we find in the S and P sublevels. Okay, so again, valence, the outermost. So we're going to look at some examples of the Lewis dot structures of the representative elements based on their electron configurations. We're going to kind of tie these two things together. So think about the 1A column: hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. We know that everything in that column is going to end in a configuration of something S1, 1s1, 2s1, 3s1, 4s1. So they only have one valence electron. So everything in that column, when I draw the Lewis dot structure, would have the symbol of the element, which represents the nucleus and any inner electrons that there might be, and then a single dot that represents that one valence electron. So hydrogen, because it only has one electron, the H represents the nucleus, the single dot represents that one electron. If we contrast that with something like potassium, potassium was in the 4A. So not only does the K represent the nucleus, it also represents all of those inner electrons, 1s through 3p, as the inner electrons, and then the valence electron, the one valence electron, is the dot. Okay? So the 2A column ends in something S2, so it has two dots. Now, when I'm looking at this, like say beryllium's going to have two dots. It's important to know that those two dots are not paired up. The reason that they're not paired up is that in the 2s level, which is where beryllium starts, and everything further down, they also have access to a P. So even though I'm not writing anything in the P, they have access to the P, so they're able to spread out. So it's important to know that they are going to be single. We are going to fill these in single before we double them up, kind of like what we saw with Hund's rule when we were filling in electrons in electron configuration. So beryllium, another example would be calcium, so 2 single dots. It doesn't matter which side you put the dots on. I like to just pick one side. Sometimes I start on the side and go all the way around. Sometimes I start on the top and go all the way around. The point is you're going to go all the way around before you double up, with one exception, which I'll show you in a minute. All right, the 3A column, so boron, aluminum, gallium, they all have something S2 and something P1. So how many dots? I hope you're seeing a pattern. They should have 3 dots. So boron, 1, 2, 3 dots. Gallium, 2, 3 dots. So the number of electrons that we're seeing here represents the number of dots we're going to have. Also consider this 1A, 1 electron, 1 dot, 2A, 2 electrons, 2 dots, 3A, 3 electrons, 3 dots. So 4A, S2, P2, 4 electrons, and you guessed it, 4 dots. So calcium or carbon, 1, 2, 3, 4. Silicone, 1, 2, 3, 4. So if we continue that pattern over in the 5A column, we're going to have something S2 and something P3, and that's going to give me 5 valence electrons and 5 dots. Now, here's where the sides do become important. Nitrogen. So when I fill in my dots, 1, 2, 3, 4, 5, notice I have a pair of dots on the top. The pair of dots on the top is really important in nitrogen and phosphorus and arsenic and antimony and bismuth because it's going to influence the shape that those elements take on when they bond. So when you draw the 5A column, those dots need to be on top. Okay. 6A column, something S2, something P4. So 6 electrons, so oxygen, 6 dots, 1, 2, 3, 4, 5, 6. And selenium, 1, 2, 3, 4, 5, 6. 7A, something S2, something P5. 7 dots, 1, 2, 3, 4, 5, 6. 7, and iodine, 1, 2, 3, 4, 5, 6, 7. And then that leaves us with our last column, our 8A column, that we know is something S2, something P6, has 8 electrons, so neon. And we always speak about these noble gases having a full outer shell. Another way to describe it is a full octet. A full octet referring to 8 electrons in the outer shell. All right, so that works for neon, that works for argon. Who does that not work for? It doesn't work for helium, right? So helium only has 2 electrons. What is helium's configuration? Well, it's 1s2. Because it's 1s2 and there's no 1p, when I draw the electron orbital diagram, the Lewis dot diagram for helium, I can't spread out the dots, right? There's no extra places for there to go. There's no P for me to fill. So with helium, helium's the only exception where the dots have to go in paired, and a full shell for helium is 2 dots. Remember, all my other noble gases have more than 8, so they can have an 8 full outer shell, right? Neon has 10, argon has 18, krypton has 36. Helium only has 2. And if it only has 2, then wouldn't 2 be a full shell for helium? So that there's my paired electrons for helium. All right, so we're going to talk about how those electron dot diagrams now relate to the shapes that we're going to see. So we're going to go through examples of looking at each column, what the central element would be, and what the shape would represent. Now, notice that I'm starting over with the 3A column. I can do Lewis dot diagrams for every element on the periodic table, but I'm talking right now about covalent molecules. And so that means I'm only really going to deal with the nonmetals. So I'm going to start talking about boron because boron is the first nonmetal in my 3A column. And I'm not going to start talking about hydrogen because hydrogen is only able to make one bond. So if it's only able to make one bond, it's not really going to be a central element. It's going to bond with other things to complete their octets. So we're going to start with boron, and boron is our only 3A. So I'm going to draw its dot diagram, which we just saw on the last page. 3 dots. All right, and it doesn't matter where they go, just they have to be single. Boron forms a shape that's called trigonal planar. Okay. And its shape structure looks like this. With the boron in the middle, I'm going to have 3 bonds at equal angles coming out. So let's talk about bond angles. It's not necessary at the honors level of chemistry to know the numerical value of these bond angles. That's something that we know in AP chemistry. But what you do need to understand is that these lines that I'm drawing represent the bonds that are occurring. Well, the bonds are made up of electrons. What do we know about electrons? They're negatively charged. And 2 things that are negatively charged are going to repel. So the bonds arrange themselves in such a way that those electrons can be as far away from each other as possible, yet still being bonded to that central element. So we're equidistant on all of these from each other, and they're still bonded. Then we talk about the polarity. In general, the polarity. When boron is in the middle, we're going to have equal pull in all directions. So in general, we're going to say that this is a nonpolar structure. Okay. And I'm saying this in general because depending on which elements I have attached to that, that could change. But in general, equal pull in all directions. All right, so now we're going to go to the 4A column. So carbon and silicone in the 4A column are kind of unique. They are able to make 2 different categories of bonds. So we're going to start with the simplest one first. So carbon and silicone have 4 valence electrons, and they can use those 4 valence electrons to form 4 single bonds. And when they form 4 single bonds, they make a shape that's called tetrahedral. Okay, and think about what we saw when we did our nomenclature. Tetra means 4, so 4 bonds, tetrahedral shape. And when I draw that out, I've got the carbon or the silicone in the middle, and I have my 4 bonds coming out at my angles. Okay. Again, as far away from possible. It's hard to see because I can't draw in 3 dimension, but they're spread out. And in general, this is a nonpolar shape. Okay. Remember I said it varies based on what's actually attached. We're going to see some more specific examples in a minute, but in general, equal pull in all directions. The other shapes that carbon can make and silicon can make is going to depend if it makes a multiple bond. So carbon also has the ability to make, and frequently does make, a double bond. Okay. When it makes a double bond, the shape that it takes on at that point is called linear, or a straight line. Right? So we'd have the carbon double bonded to something, okay, and also double bonded on that side. So it's still 1, 2, 3, 4 bonds. They're just rearranged differently. So 4 bonds, 4 bonds. Also nonpolar, okay, in general structure. And really, we see anytime that something is going to make a multiple bond, whether it's a double bond like we see here with carbon, or even carbon has the ability to make a triple bond and a single bond, it's still going to be linear. Anytime you have a multiple bond, it's going to force you into a straight line. It's just a little bit more common with carbon to see tetrahedral and double bond linear. Triple bonds you don't really just see as often. All right, the 5A column, the nitrogen, phosphorus, arsenic column. So remember when we were doing those electron diagrams on the last page, I made a particular point to say that the unshared pair in nitrogen has to be on the top. Well, I said because it influences the shape. The shape it makes is called pyramidal. And that is because, quite obviously, it looks like a pyramid. So when I put my pair on top, that forces the other bonds down. This pair, it doesn't look like it from the way I've drawn it, but in reality, it takes up a significant amount of space over top of our nitrogen. Okay? And it pushes those bonds away. It repels them because, again, negatively charged, so it's pushing them away. The presence of this unshared pair of electrons over here makes this molecule polar. So it's the presence of the unshared pair of electrons that makes this polar. Then we have the 6A column. In the 6A column, so oxygen is a good example. We have 1, 2, 3, 4, 5, 6. 6A column, we're going to form a shape here that's called bent. Same thing, I'm going to have my two now unshared pairs taking up a tremendous amount of space and really squishing those two bonded pairs down. And it takes up a lot of space, a lot of room again, and it's going to change the angle of those two bonds. The presence, once again, of the unshared pairs is going to make this a polar bonded compound. And then the last column, the 7A column, our halogen column, fluorine is a good example, has 7 valence electrons. And with 7 valence electrons, it only has the space, the opportunity to accept a single electron. So it can only form one shape. If it's in the middle, it's going to be linear. It's going to form a straight line. And with this column, it's a little interesting. This column, because it can only form these straight line shapes, it really matters on what it's paired with, what the polarity is going to be. It can actually be polar or nonpolar. And the reason why it can be both is the things in the halogen column have the likelihood or the strong likelihood of bonding to themselves. And so if you think about it, polarity is based on who hogs the electrons. If you're bonded to an exact copy of yourself, you can't hog the electrons any more than you could, right? So they would have to share them equally at that point. So if bonded to itself, we're nonpolar. If bonded to something else, it's probably going to be polar. So I'm going to stop this video here. And I'm going to start a new recording where I go through some shapes and some examples of shapes with specific compounds. This one's getting a little bit long, so I don't want to go on too long with this. But there will be another video following this that goes into some specific examples of how to draw shapes of specific compounds, not just the general shape structures that we see here.